Alright, so we have a pretty simple definition. The sum of EMFs is equal to the sum of potential differences in a closed loop. That's it for the definition. Sum of EMFs equal the sum of PDs in a closed loop. So mathematically I can write it this way. The sum of all the EMFs equals sum of PDs in a closed loop. And this law, the Kirchhoff's second law or voltage law, is based on the law of conservation of energy. They asked you this one in paper 1. Now keep it in your mind. When we use the word EMF, that usually it refers to the voltage of the battery or the cell or the power supply. So voltage of source, the source of the electricity. It could be a battery, could be a it could be a battery, it could be a power supply, it could be a cell. And when we say the potential difference, so usually it is a voltage across current consuming device. And what do we call the current consuming device? Could be a resistor. And when I say the resistor, it could be anything. It could be any device that consumes current. Or we can say the energy consuming device. The device across which power is dissipated or power is lost. For example, light bulb, could be a fan, could be a speaker, could be a smartphone, could be a TV, could be an actual resistor also, which are made up of carbon. We use it in the physics practical. So this is what you need to memorize about the Kirchhoff voltage law. Now for this one, there are certain steps that you need to follow to solve a circuit using Kirchhoff's second law. What are those steps? So on this one, I'm going to write some of those steps which we can use to solve the circuits. Now for the first one, okay, I should be writing here on the lines. Number 1, if multiple sources are given, if we have the sources, they must be having the EMFs. So if multiple sources or multiple EMFs, multiple batteries, multiple power supplies, multiple cells are given, one of them is set one battery, one cell, one power supply out of all of those is set as a standard one or is chosen as a reference one. So there would be one chosen one. There would be one chosen power supply, there would be one chosen battery, or there would be one chosen cell. So out of all the EMFs, we'll choose 1 for reference. In the next step, okay, just keep memorizing these steps because we got to be using these in the circuits. In the next step, we label the direction of current. Label the direction of current from positive to negative of the chosen EMF, source of EMF, of the chosen battery, of the chosen power supply. Up next, write sum of EMFs on one side of the equation and sum of PDs on the other side. Most important one, the PDs for which direction of current is same as the direction of reference current will be written with positive sign on, let's say, right side of the equation, or on one positive sign on the other side of the equation. On the other side means as opposed to the side which contains the EMF. And I explain all of these with the help of an example. You'll see how we use all these steps. But for the last one, you can also reverse it. This way, the potential differences for which the direction of current is opposite to the direction of the reference current, that'll be written with the negative side on the other negative sign on the other side. Now, what do we exactly mean by that? I mean, it won't make any sense, at least so far, just going through the steps, unless we solve a circuit using these steps. And lo and behold, here we have a circuit. We already solved for the first part, but I'm going to remove all of it, at least for now. So we have the beautiful circuit in front of us over here. Yeah, and that'll be the last question. So actually, the question was, once again, like I said, I've cropped out some of the details of the question. The question was, use the Kirchhoff's law to form the relation between these quantities in the part A, in the part B. In the part B, whenever you see the EMFs and the resistances and the currents, then you have to use the Kirchhoff's second law. Kirchhoff's second law is always used around a loop. Now, what is the chosen loop? W, X, Y, Z, W. I'm going to mark this one. W to X. Check it out. W to X. Then X to Y. then y to z, and then z back to w. You see, we have a closed loop. We have a closed path which is known as a loop. What is this general expression? Sorry. Now, what was the first step? So, Manori, if you could read me the first step. This one, I don't want to scroll up. Or
So we'll choose one of the EMF as the reference.
sorry, could you repeat?
We'll choose one of the EMF as the reference.
All right, excellent. So we gotta choose one of these sources of the EMF as a reference. Now, my first question is, in the loop that you see, in the marked loop, how many sources of EMF or how many batteries do we have? And what are the names of those two batteries? I mean, answered it already. There are two batteries, and the names of two batteries is very trivial to find. It's E1 and E3. What are the two batteries in our circuit that we have labeled? Is E1 and E3. This one and this one. What about E2? The thing is, it's not part of the loop. We don't have to do anything with that one, E2. It's not part of the loop. Out of these two, we gotta choose one of the batteries as the reference. So I'm going to choose, let's say, we're going to choose this boy as the reference, this battery over here. This is the reference battery, and I'm going to mark the direction of the reference current with respect to the chosen battery. So this is the negative of the battery, this is a positive. So the direction of current in our closed loop should be this, from positive towards negative. Now we have marked the direction of the reference current also. Let us write the expression sum of EMFs on one side and sum of PDs on the other. Sum of EMFs on one side and sum of PDs on the other. Now, how many EMFs do we have? Well, the first one, you write the reference one first, E1. And then the second one was E3. Should we add this one or subtract? You see, the positive of this battery is connected with the negative of the other one, so we add the batteries. What do I mean by this? Well, if the batteries are connected like this, positive, negative, and then positive, negative, and then positive, negative, we simply add the batteries, we add their EMFs. But if their same terminals are connected together, let's say like this one is 6 volt, this one is 3 volt. In that case, we subtract the batteries. We subtract the batteries means we subtract their EMFs. But luckily for us, they are connected the right way. So their EMFs are added. Do we have any other EMF? No. Let's go to the right side of the equation, which is the potential difference. So how many potential differences would be there? The potential difference would be across the energy consuming devices, which is like for 99.99% of the times just stay in the form of a resistor. So how many resistors do we have? Well, we have 3 of those. 1, 2, 3. You can start with any of it. I mean, I can start moving from this pathway from here. So I go downwards because the direction of the current is clockwise. The standard one is clockwise, so I'll go clockwise. Now in this one, the first potential difference would be across R1. How much current is flowing through R1? It's I1. So what is the voltage or the potential difference across R1? It's I1 R1. And it's written with a positive sign. Why with the positive sign? Because the direction of this current is same as the direction of the reference current. Otherwise, it would have been written with the negative sign. Let's say I1 was upward. Then the direction of I1 would have been against the direction of standard or the reference current. It would have been written minus I1 R1, which isn't the case, at least for now. In the next question, it could be a case. So we write it as I1 R1 with a positive sign. So I've gone past this point. I don't have any other resistor here. So I keep walking, I keep walking, I keep walking here. I cannot go in the middle because that's not part of the loop. Then I pass through this one. Now there would be some voltage across R3. What is the potential difference across R3? It would be I3 R3. Why? Because if I trace this current I3 is passing through R3. And the direction of this current is same as the direction of standard current. So I write it with the positive sign. I3 is clockwise. My standard direction is also clockwise. So positive. Now let's continue. What about this one? I keep walking. I've crossed this point now. I move over here. I find another resistor in the path. How much is that? The value of the resistance is R4. The value of the resistance is R4. How much current is passing through that one? If I trace this current, I3, then it's the same current that would flow through here. So what is the voltage difference across, or what is the potential difference across R4? It is I3 R4.